Hello, my name is Andreas Filipp and I'm a PhD student at the University of Montreal in my last year. Today I will present about dark matter subhalos in the context of strong gravitational lensing, a topic that runs through all the projects of my PhD. Our motivation behind using strong lensing to study dark matter subhalos lies in challenges of modern cosmology. The standard model of cosmology, the so-called lambda CDM model, predicts the presence of dark matter. In this model, approximately 1/4 of the total energy budget of the universe is present in dark matter, 70% in dark energy, and only 5% in visible baryonic matter. There are many observational probes of dark matter, like the requirement of dark matter in observed galaxy rotation curves, or the requirement for more mass than visible matter can provide to explain gravitational lensing effects. But still, the nature of dark matter and its particle properties remain unknown, and on small scales in the universe, the lambda CDM model does not predict what we can observe. For example, lambda CDM predicts more light mass halos and satellite galaxies than we see. This is the so-called missing satellite problem. The contradictions on small scales are directly related to the dark matter particle properties. First, if we can study the behavior of dark matter on small scales, we can also infer the particle properties of dark matter. Gravitational lensing arises as a powerful tool to do that because it's a pure gravitational effect and therefore it's an independent probe of dark matter. In gravitational lensing, the light of a background object gets distorted by a lens in the foreground, and the distortion is dependent on the total mass, visible and invisible mass of the lens. But let's start with what we already know about dark matter and how we infer those informations, even though dark matter is non-visible. First, the only known interaction path with visible baryonic matter is through gravity. And one observational probe of dark matter are galaxy rotation curves. In the 70s, Vera Rubin and Ken Ford observed galaxy rotation curves and realized that the observed rotation speed can only be explained with additional non-visible mass. This you can see illustrated on the top, where the red shows the rotational velocity of a galaxy over the radius, as it is predicted by only visible mass. And the white shows the actual measurement of that rotational velocity over the radius of the galaxy. Another way to probe is through simulations, because the observed large-scale structures in the universe can only be simulated and modeled with inclusion of dark matter. And a further observational probe of dark matter is gravitational lensing. A famous example for that is the bullet cluster, shown here on the bottom right. The green contours show where the mass of the bullet cluster needs to be to explain the lensing effects, while the yellow and red areas show where most of the baryonic mass is actually located in the cluster. So, what do we know about dark matter from those probes? We do know dark matter interacts only through gravity, and we do know that dark matter builds clusters and structures analog to baryonic matter, and the clustering behavior of dark matter does directly depend on its particle properties and its temperature. The biggest discrepancy to the standard model of cosmology is the clustering behavior on small scales, which can be effectively probed through gravitational lensing. In the following, I will explain what gravitational lensing is. So, gravitational lensing occurs when the light from a background source gets bent by the gravitational potential of a foreground object, and it appears at a different position on the sky than it actually is. This is illustrated in the image on the right here. In this sketch, the sun acts as a lens, and the light of a star behind the sun gets deflected. The deflection occurs due to the curvature of space through mass, which is predicted by Einstein's general relativity. And the first observation of a gravitational lensing effect was made by Arthur Eddington in 1919. During a solar eclipse, he observed a star in a position in the sky that it shouldn't be in, so the position got distorted by the mass of the sun. Gravitational lensing in general can be categorized into different regions depending on how strong the lensing effect is. For our case, we are interested in strong gravitational lensing, which is the limit of observing multiple visible images of the same background object around the lens. The effect of strong lensing is very similar to the propagation of light through an optical lens. This is shown here in the images on the right side. If the bottom of a wine glass is held at the right angle to a candle behind it, we can see a ring of light in the glass, through the glass. And depending on how we incline the glass, we do see the candle multiple times. For strong gravitational lensing, the wine glass is a massive galaxy, and the candle is a different light source, for example, a different galaxy at higher redshift behind it. The alignment of lens and source, as well as the mass of the lens, define the shape and appearance of the deflection. So in reality, we have, besides a smooth main deflector, multiple small mass halos that act as lenses and affect the light path of the background source. Those small halos without any visible counterparts are so-called dark matter subhalos, which are well simulated in different large-scale simulations. The distribution of those subhalos, so the mass function, depends on the dark matter particle properties. So probing the distribution of the halos and their masses allows us to draw conclusions on the natures of dark matter. Each dark matter halo affects the light of the background source, but it's a very, very small effect in comparison to the main deflector. The dark matter halos have a very weak effect on the observations, which makes them very hard to detect, and so far 2 direct detections of dark matter have been made with strong gravitational lensing, one in 2010 by Simona Vighetti and one in 2016 by Yasha Hisavi. On the right side, there are 2 simulated strong lens images with the same main deflector, but one of these images is populated with dark matter halos, and by eye it's basically impossible to tell the difference between those images. So, to show that these images are indeed different, here is the difference between those 2 images, and you can see that at the Einstein ring, there's a weak effect of the dark matter halos, but from the images alone, we cannot tell that the upper one is simulated with dark matter and the lower one without dark matter. This shows that the signal of dark matter is typically so weak that it cannot easily be observed. One way to test a subhalo population with strong lensing is to amplify the weak signal by not using one strong lens, but by using many strong lenses. Currently, we know around 1,000 strong gravitational lenses, but with future surveys, like the Large Synoptic Sky Survey, LSST, or also Euclid, the number of strong lenses is poised to increase to approximately 150,000. That big amount of lenses can then be used to infer the dark matter clustering behavior and the dark matter particle parameters. Another way, which we also talk about today, is obtaining the information about dark matter subhalos through a very precise analysis of an individual lens and comparing the measurements to theoretical predictions. But let's start with probing dark matter on a sample of lenses. At this detection path, we can combine the signal of many observations, and we want to use machine learning methods to extract the signal of all those observations at the same time. In our project, we classified between different dark matter parameter realizations by using a big set of simulated lenses under the same cosmology. We simplify the dark matter mass function to draw the mass and dark matter halos from a simple power law, such that that our dark matter properties depend on only 2 parameters. One would be the slope beta of the power law, and the other one is the ratio of mass in dark matter halos to the total mass in the main lens that we call f sub. Here on the side, you can see different realizations of those simulations. The first column shows the normalized surface density of the main deflector. The second column, the normalized surface density of the dark matter halos. And the third column, the unlensed background source. The fourth column shows the resulting lensed image without noise, and the last one, the lens with observational effects and noise. We sample the dark matter halos only for masses between 1 to the power of 7 and 1 to the power of 10 solar masses, And that's why the last row with a very flat mass slope appears to have the least halos, even though it has the highest ratio of mass in dark matter halos. What we basically wanted to is to classify between different dark matter parameter realizations. So we can use a so-called neural ratio estimator to obtain the likelihood ratio of different dark matter realizations. The neural ratio estimator learns to marginalize over all different lens model parameters like the source, the Einstein radius, or other, and the noise, and it tries to find the signature of different dark matter realizations independent of the main lens model and the source. This allows us to infer the posterior distribution of dark matter parameters through an ensemble of lenses that share the same dark matter model. This method works efficiently and well when the data at test time is exactly in distribution with training data. The signal of the dark matter subhalos is so weak that smallest differences in the training distribution can bias the network unpredictably. We show that possibility of those biases in our paper, and we saw that even minor variations, like drawing the Einstein radius from a different distribution within the same bounds as the training distribution, increases the biases of induces biases to the network's predictions. So another way to get around biases effects in those networks could be to use single observed lenses and analyze them in great detail to put observational constraints on its subhalos. So strong lensing is sensitive to all mass again, so the subhalo distribution can be observationally constrained. So far, only a few direct detections of single dark matter halos in lenses have succeeded. So the path of having a few strong individual constraints on the subhalo mass function could be a more promising path to constrain the nature of dark matter than using many strong lenses with the possibility of inducing biases through wrong assumptions during training a neural network. With observational constraints, one now only needs to compare the measurements to different dark matter theories. A common often used possibility for that is the warm dark matter theory, which expands cold dark matter subhalo mass function with a mass cutoff that depends on the warm dark matter mass. At masses lower than the mass cutoff of warm dark matter, the predicted number of subhalos goes down again, which affects a peak at the here called parameter MWDM. A comparison with theory on a single galaxy scale is not that straightforward. The mass function of each of the subhalos of each single galaxy that is a strong lens has a dependency not only on the warm dark matter mass, but also on the lens environment, the galaxy structure, the Mercer history, and other effects that are specific to each galaxy. So within the same cosmology, the subhalo mass function of an individual galaxy can differ strongly to another galaxy. Therefore, we aim to find a way to predict the subhalo mass function using only an observed image of a galaxy and the assumed warm dark matter mass. This information would be also accessible for any observed strong lens for which we have constraints on the dark matter subhalo mass function. In our project, we use hydrodynamical simulations with different dark matter models to learn the relation between the dark matter model and the galaxy image given the mass of the warm dark matter. We create realistic looking galaxy images from the simulation data, and we train a neural network to predict the galaxy specific dark matter subhalo functions. And for training our network, we use the subhalo mass function directly constrained by the simulation data that we have access to. Here on the right, we show examples of fitting the mass function from a simulation. So from the simulations, we get the binned mass function, which are the black dots. And to that, we fit the warm dark matter model within MCMC. The results of that fit are shown in blue in the plot. and we train a neural network to learn that those fit parameters to only then take the image in the warm dark matter mass to output the subhalo mass function fit. Those results are shown in red in the plot, and they do agree well with the direct fit to the data. We submitted our preliminary results to the Machine Learning for Astro workshop hosted in Vancouver this summer. So in summary, we can say that an increasing amount of astrophysical data will help to shed light on the nature of dark matter, and LSST and Euclid will play an important role in that. And strong lensing emerges as a powerful tool and independent measurement of the mass distribution and can probe dark matter on small scales well. Even though individual dark matter halos are difficult to detect, future surveys will help to build an understanding of dark matter properties, since the big amount of data allows to amplify the weak signal through the use of an ensemble of strong lenses. We use a neural ratio estimator, which is a powerful tool to gain these population parameters while marginalizing over all individual lens parameters, but we discovered strong drawbacks that make the neural ratio estimator hard to use for analysis of real data. Individual dark matter detections with strong lenses are possible and can also help shedding light on the nature of dark matter, but comparing observational constraints on single galaxy scale to theoretical predictions is not very straightforward, because the theoretical predictions in the same cosmology can vary a lot between different galaxies because of the dependency on many galaxy properties. First, we learn the relation between the theoretical predictions through a hydrodynamical simulation and observed galaxies with machine learning. Our current results are limited to a small and biased sample size in the simulations, but they give us a promising path that can hopefully then be used with increasing detail and amount of cosmological simulations. So thank you for listening.